Now, hi everyone. I want to present a solution to a problem from Terence Towns' book, exercise 2.23. This problem states that if f is a continuous function on a metric space, that if we take the absolute value of that function, that is also continuous. So before starting the proof, it makes sense to clearly state what is the assumption. This does not need to be part of the proof. We will use it, but it is visually helpful to know exactly what it means. Every point, no matter what epsilon you choose, there exists a delta such that points close enough mean that the function value is close enough. And here the distance is the distance in R, meaning the absolute value distance. And I added little subscripts here because in this proof I want to be careful that there are different epsilons and deltas, and I want to be choosing them very carefully because there are the epsilons and deltas relating to the proof of absolute value of f being continuous, and then there is the epsilons and deltas using the definition of f, and we will use those with different ones. So suppose f is continuous. That is this is our setup phase, and we are assuming that here, so let's suppose that. Let's fix a point and fix an epsilon. This is setting up the proof of the continuity of f prime. Okay, so this is the setup phase. Next, we have to do the choice. And it turns out, after the fact, that choice of delta equals delta f works. So now we have to, after we've done that choice, we have to show that it actually works. And the small remark here is that how do we make that choice? Well, we're applying the definition with epsilon f is equal to f and x is equal to x. So there exists a delta f. Because it exists, we can choose one of them that holds. Okay, so let's now show that it works. Now we use absolute value of f at x is equal to absolute value of f of x. Let's start from the assumption. The point is close enough. dxy is less than or equal to delta. This means that because delta is equal to delta f, the distance is less than delta f. And by assumption, it means that f of x is close to f of y. This is not quite our claim yet, because we're saying that absolute value of f of x is close to absolute value of f of y. So we want to estimate this difference. But this difference is always less than, by the reverse triangle inequality, than absolute value of fx minus fy, which we just said is less than epsilon. So the proof is complete modulo saying something about this reverse triangle inequality. And there, what we're using is that for any real numbers, absolute value of a minus absolute value of b, absolute value is less than absolute value of a minus b. And here, this is our real number, a is f of x, and our real number b is f of y. And that concludes the proof.